Hello, I'm Junan Seo. I'm very pleased to make this presentation at the JMAG 2020 conference. My topic is Recurdine dynamic simulation of drivetrain system with electric motors. The contents of presentation is as follows. First, I will introduce our product Recurdine. I will explain the Recurdine drivetrain toolkit such as gear, bearing, shaft generation, and through an example model using the Recurdine drivetrain toolkit and JMAG motor, I will introduce the dynamic simulation of motor model and mechanical system. Recurdine is multi-body dynamic simulation software. It can predict the behavior of mechanical systems in the time domain. Recurdine is able to simulate complete mechanical systems, and Recurdine can simulate a single component of mechanical systems too. Recurdine can simulate several seconds to tens of minutes of motion. In most dynamic models, contact must be simulated. Recurdine is able to simulate contact robustly and accurately. Recurdine has the ability to simulate finite element flexible bodies in the same model as rigid bodies. Recurdine can also co-simulate with other software for control and motor model generation. Through these capabilities, user can produce complex multi-domain results. For most mechanical systems, dynamic behavior is essential. These dynamic behaviors can be easily modeled and simulated using Recurdine's robust solver and intuitive GUI. The videos show the various fields of application that Recurdine is used in. There are systems commonly used in various industries. Most of these mechanical systems contain components that drive or power the motion of system. These drive systems have different sizes and configurations depending on their purpose, but are typically made up of a combination of basic components such as gears, bearings, and shafts that deliver power and support loads. Recurdine drivetrain is a product, models, and simulates the components of drivetrain. For example, it can model gears, bearings, shafts, and other components. Recurrent drivetrain consists of three toolkits: gear kit soft, bearing kit soft, and shaft. This toolkit makes it easy for users to model, simulate, and analyze drivetrain systems with gears, bearings, and shafts. It has a specialized solver and many dedicated post-processing features. A couple of aspects of Recurdine drivetrain are important to this presentation, in particular, gear keysoft and bearing keysoft. This has been developed through the technical partnership with Keysoft, which is a part of Gleason. These elements allow Recurdine to accurately model various gear and bearing parts. Gear keysoft and bearing keysoft include libraries of thousands of gears and bearings. Using gear keysoft and bearing keysoft, it is possible to simulate transmission error for noise and vibration evaluation. Using the Recurdine drivetrain toolkit, a transmission reducer gears can be modeled. It is possible to simulate the torque of an electric motor. Drivetrain characteristics are below. Keysoft is a tool to model drive systems. Keysoft models the contact forces between gear teeth. Keysoft calculates the force based on the shape of the gear teeth. Keysoft also models the stiffness of bearing elements. Recurdine has a direct interface with Keysoft. During a simulation, Recurdine sends the positions of gear and bearing elements to Keysoft. Keysoft calculates the force between elements and gives the force to Recurdine. Keysoft predicts the force very accurately. If flexible bodies are used, then the dynamics of the complete drivetrain can be modeled. For example, the gearbox housing can be modeled as an R-flex body. R-flex body use modal reduction. The drive shaft could be modeled using full-flex. Full-flex is finite elements with full nodal degrees of freedom. Then the complete drivetrain can be modeled very accurately. Then the vibration and boom misses stress can be determined in the flexible bodies. Then NVH results can be also calculated using Campbell diagrams or acoustics in Recurdine. There are 6 advantages of Recurdine drivetrain. The first advantage is analytic gear contact. Analytic gear contact is very accurate. The second one is a simple GUI. It is very easy to create a model using the gear and bearing shaft modeler. The third advantage of Recurdine is a big library of bearings. The fourth is that the gear system can use flexible bodies. The fifth means that transmission error and misalignment of gears can be simulated under various conditions. Lastly, user can check the results in the time domain and in the frequency domain using post-processing tools. I want to show you an example of Recurdine drivetrain with gearbox model. Here is a model of gearbox reducer system. This gearbox including helical gears and planetary gears. There are 18 teeth on the driving gear and 17 teeth on the driven gear of the helical gears. The reducer system also have one set of planetary gears. So total gear reduction is 24 to 1. In addition, there are 11 bearings contained inside the planetary gears and on the shafts. The bearings are modeled to be from various manufacturers like SKF or Schaeffler. The input shaft has a user-defined motion. The shaft rotation speed increases linearly from 0 to 4000 RPM. A counter torque is applied to the output shaft. The counter torque is 2000 Nm in the opposite direction of the rotation. This is the typical modeling process for creating a drivetrain model. Generate the gear, bearing, shaft components using each modeler in Recurdine, and then define the contact elements and simulate the model. After the simulation, the transmission error, contact force, and changes in gear variables over time are checked with the result of gear contact force. Once the drive system is modeled to gear contact, housing of gearbox is converted from rigid to nodal flexible body and modal flexible body. Through the total process of modeling, results for frequency domain can be viewed through the Campbell diagram and checked for resonance. Using the vibration information of housing, check the MVH and acoustics results. This all typical process of simulation can be implemented in Recurdine. Here is a video of the reducer simulation results. From the video, we can confirm that the forces looks reasonable. The contact forces between the helical gears spiral in a helical pattern along the teeth. We can also verify the speed reduction of the sun gear from the plot. This model includes gravity, and gravity causes the contact force to change in different position. Maybe you will think this is surprising, but the highest contact force occurs at the point when the planetary gears are at the highest position. It is possible to examine the results to verify if the simulation is reasonable. We can verify if the characteristics of the gears have been modeled well. To check this, we can use the gear mesh frequency we called GMF. The gear mesh frequency is the frequency of the gear tooth engagement. Using the GMF, other important things can be predicted. For example, using GMF, we can predict gear backlash, eccentricity, or misalignment issues. The gear mesh frequency is RPM multiplied by this number. So we can calculate this analytically. It is a simple calculation. In this model, the GMF on the first shaft is 1200 Hz, and the GMF on the second shaft is about 184 as shown in the right side table. We can use these to verify the results of Recurdine model. The transmission error from the simulation is in the time domain. This can be converted to the frequency domain by taking the FFT of it. The FFT shows a high amplitude at 1200 Hz. This is the largest in the transmission error, and it is from the helical gears. And there are also many harmonics of 184 Hz. 184 Hz is the GMF excitation frequency from the planetary gear system. So the Recurdine simulation results are a good match with the analytic values we previously calculated. Also, if you look at the result in the time domain further, there is some much smaller amplitude shapes that appear repeatedly as the gear rotates. So with Recurdine drivetrain toolkit, you can analyze both macroscopic and microscopic results. It is also possible to find the natural frequency of the total gear reducer system using Recurdine. The natural frequency of the housing can be compared to the operation frequency to check if reducer gears will cause large vibrations in the system. The flexibility of the housing is very important to the natural frequency of the reducer system. So the flexibility of the housing must be included in the model. Therefore, we must convert a housing body to a flexible body. To convert a housing body to the flexible body, we can use Recurdine eigenvalue solver. The eigenvalue solver will find the vibration mode shapes of the housing body. These mode shapes are used to create an R-flex body in Recurdine. R-flex means reduced flex, which is a kind of flexible that uses vibration mode shapes. After the housing body has been converted to an R-flex body, we can find the vibration frequency of the total gear reducer system. We use another Recurdine eigenvalue solver to do this. The result of this is the vibration of the total system and system natural frequency. If we do this, we can see that the lowest vibration frequency of the reducer system is 581 Hz. Until now, I have been preparing a dynamics model of reducer system that uses a modal flexible body. Then let's combine the Recurdine model with a JMAG-RT motor model. Performing a co-simulation between Recurdine and JMAG-RT has two steps. The first step is to import the JMAG-RT motor model into Simulink. The second step is to import the Recurdine mechanical model into the Simulink JMAG-RT model file and then change the mechanical numeric block into a Recurdine block. Recurdine supports a direct interface with Simulink, and Recurdine also has a specific block in Simulink. Therefore, if we use these two steps, a JMAG motor model and Recurdine model can be combined. At this moment, a closed-loop controller is necessary to get mechanical data feedback to the JMAG-RT model. Therefore, the controller is designed to convert the three-phase current and voltage to two-phase current, and the D-axis current is set to 0. By building a model to control current and speed using PI controller, motor model can also control the RPM of the actual rotor to follow the target RPM. And the mechanical system block needs to be changed from a simple inertia block to a Recurdine block, as I mentioned before. This picture on this slide shows the block after it is changed to a Recurdine block. During each step, the position and velocity information of the input shaft is delivered to the JMAG motor, and JMAG-RT motor delivers torque data to Recurdine. Then, let's find the motor model. Before applying the motor to the gearbox model, the motor capacity must be selected. First, simulate the Recurdine model from 0 to 4000 RPM using the Recurdine user-defined motion. This motion is specified in the leveled joint in the Recurdine model. After the simulation, the user sees how much driving torque is required to rotate the model to 4000 RPM. In this example, 90 Nm of torque were required to accelerate to 4000 RPM. In the JMAG-RT example, I found the PMSM 100 kW motor model, and this model average torque is 177 Nm, and this maximum RPM is 9000 RPM. These conditions satisfy my gearbox model, so I co-simulate it using this gearbox and motor model. Here is a Campbell diagram of the results. A Campbell diagram is a signal processing method which can be applied to the mechanical systems that have rotors. The Campbell diagram is used to analyze the changing vibration characteristics of the system over a range of rotational speeds. As RPM increases, you can see what frequency components appear and how vibration characteristics change. In the figure below, you can see that x-axis is RPM, y-axis is frequency, the z-axis is amplitude. First, I will examine the result from the perspective of mechanical system. Acceleration results at 2 points in the housing are used to identify the order line, which increases frequency as the RPM increases. You can see that each order line grows bigger when it passes specific frequency. This frequency indicates that the amplitude increases when the system frequency and operating frequency are close to each other. System frequency were determined previously using Recurdine eigenvalue analysis. The effect on the motor can also be seen through the Campbell diagram. The left diagram does not include the motor model, and right one includes the JMAG motor co-simulation model. The left diagram shows a large order line at 18 and 36 in proportion to the 18 in helical gears. The results on the right side shows 36 larger and 72 and 108 more. The reason is that the JMAG motor model has 12 poles and a 3-phase motor, so you can see 36 times the order. If the natural frequency of the mechanical system is 1000, resonance will occur as the motor accelerates. The natural frequency and the motor frequency will cross. This kind of resonance can be analyzed through Recurdine. Additionally, when the inverter is included in the JMAG motor model, the switching frequency is also included in the torque component. This can be seen in the results. In the terminal voltages generated by PMSM switching, the switching frequency, the multiple components of switching frequency, and the harmonic components of the sideband appear. These components can be mixed with mechanical systems to analyze how the behavior of mechanical systems changes. In this figure, switching carrier frequency is 6000 Hz, and the effect of inverter can be seen. JMAG-RT and Recurdine have the following advantages: resonance prediction, caused by the combination of the mechanical vibration and the torque lift generated by the motor and inverter is possible. Also, the capacity of the motor combined with the mechanical system can be checked through Recurdine, and malfunction can be detected when excessive load input occurs. You can check the power efficiency and the maximum RPM required for the operation of the machine system. This is the end of my presentation. I hope that this presentation will give you a good idea about identifying the problems that may arise from your motor model combined with an actual mechanical system. Thank you.